In question number 11, it says that a mass m supported by a massless string wound around a uniform disk of mass m and radius r as shown in the figure. If the string does not slip on the disk, then torque on the disk is. So again, in this kind of question, our first step should be the free body diagram. So if I draw the free body diagram of this mass m, so this mass m has one force mg that will be vertically downward, and the other force due to this string, that will be the tension. And on this disk there will be two forces, one due to this tension T and other due to this, that will be T dash, and one more force, that is the mass mg of the disk. So we need to calculate the torque on the disk. So let's say this is a center C of the disk, and we can say that this mg and this T dash is passing through the center. So we can say that the torque of the T dash about the center and the torque of the mg about the center must be equal to 0 for the disk. I am talking about for the disk. So there will be the torque of only one force, that is this tension T. So we need to calculate the torque of the T about the center. So we need to calculate this. So to calculate this, we first need to calculate the tension T. Let's say we write the force equation for this mass m. So that will be mg minus T, and let's say this m moves with acceleration a vertically downward. So we can write mg minus T must be equal to ma. So this is our first equation for this block. Now if I write the equation for this disk, so this disk does not have any translational motion, it has only rotational motion. So we have to only write the torque equation for this disk. So if I write the torque equation, so T is acting at this point and the perpendicular distance is r, so we can say that the torque will be Tr must be equal to I alpha. And what is the moment of inertia of this disk? So since this is a uniform disk of mass m and radius r, so moment of inertia will be mr square by 2 into alpha, right? Now question says that string does not slip on the disk. So if the string does not slip on the disk, so we can say that this acceleration and the acceleration of the periphery of this disk, that must be equal to r alpha. These two must be equal because string does not slip on the disk. So we can say that A must be equal to R alpha. So we have got three equations. This is the second equation and this is the third equation, right? So if I solve these equations, let's say we put the value of A is equal to R alpha in equation 2. We will get TR will be equal to M by 2 into RA. And since both has R, so this RR will cancel out. And what is the value of MA? So we know the value of MA is mg minus T. So we will get mg minus T by 2 because of this MA. So if I solve it, we will get 2T is equal to mg minus T. So that means T will be equal to mg by 3. So that is the tension in the string. So we can say that the torque of the T about the center will be equal to tension in the string into R, and that will be equal to mg by 3 into R. So we can say that our option number 2 will be correct. Now let's move to the question number 12. In question number 12, it says that a uniform rod of mass m and length L hinged at its end is released from rest when it is in horizontal position. The normal reaction at the hinge when the rod becomes vertical is. So this question says that let's say there is a horizontal uniform rod of mass m and length L hinged at its one end. So let's say this is hinged at this point O, right, having mass m and length L. It is released from rest. So we can say that initial angular speed will be 0. So this will be the initial angular speed of the rod. Now question says that normal reaction at the hinge when the rod becomes vertical. That means finally the rod becomes vertical like this. So if the rod becomes vertical, so it must have rotated through this angle pi by 2. So we can say that it must have acquired some angular speed, let's say omega naught, right? So as we can see that there will be a normal reaction at this hinge point. We can see that there will be two forces acting on this rod. One is the mg, which is acting at the center of mass of the rod, and other is the normal reaction due to this hinge point, right? So as we can see that this point O does not move at all. The displacement of this point O is 0. So we can say that the work done by this normal reaction will be equal to 0. And this center of mass moves from this point to this point. So we can say that the displacement of this center of mass along the vertical direction, that is H, will be equal to L by 2. So work done by mg will be equal to mgh, that means mg into L by 2. So these are the work done by these two forces, normal and mg. And we know that the total work done on any system will be equal to the change in kinetic energy, right? Half I omega final square minus omega initial square. This is the change in kinetic energy of this rod, right? So work done by normal is 0. Work done by mg is mg L by 2. Half I. What is the moment of inertia about point O? That is ml square by 3. And what is omega final? Omega final is omega naught. And what is omega initial? Omega initial is 0, right? So by this solving this, we can say that omega naught will be equal to square root of 3g by L. So this is the angular speed of the rod when the rod becomes vertical. Now if I want to find the angular acceleration alpha of the rod at this vertical position, so we should use the equation torque is equal to I alpha for this vertical position, right? And in this vertical position, mg will act in the vertically downward direction and normal acts from this point. So if I want to write the torque about O at this point, so the torque of the mg, because mg is also passing through this O and normal is also passing through this point O, so we can say that the torque about O at this point will be 0. So we can say that alpha at this point will be 0. So in the vertical position, omega naught is root under 3g by L and the alpha is 0, right? So now we know the angular velocity and angular acceleration at this vertical position. Now if I redraw this rod in vertical position, so this is the vertical position and we found that it has omega is equal to square root of 3g by L and alpha is equal to 0 in this vertical position. And we know that this center of mass will be at a distance L by 2 from this O hinge point. So we can say that the acceleration of this center of mass will have two components. One is along the tangent, that will be R alpha, that means L by 2 alpha, and one is towards the center, that is omega square R. So omega square L by 2, this will be the normal acceleration. And since tangential acceleration is 0 because alpha is 0, so we can say that the acceleration of the center of mass will be equal to omega square L by 2 and that will be equal to 3g by 2. So this is our acceleration of the center of mass. And since this acceleration of center of mass is in vertical direction, why? Because this AT is 0, so only AN will be there and that is vertically upward. And there are two forces acting on this rod at this point. First is the normal reaction and second is the mg. So if I write the force equation for this rod, we can write normal minus mg must be equal to MACM, right? So if I put the values, N minus mg will be equal to M into ACM is what? 3g by 2. So by solving this, we will get N will be equal to mg plus 3 mg by 2. So we will get 5 mg by 2. So we can say that our option number 2 will be correct. Now let's move to the question number 13. In question number 13 it says that a particle of mass m is projected from surface of earth with kinetic energy E. If particle is reached up to maximum height r, then value of E is. So question says that a particle is thrown from the surface of earth with kinetic energy E, right, and it goes up to height r. Since at maximum height the velocity of the particle will be 0, so we can say that the final kinetic energy must be equal to 0, and initial kinetic energy is how much? E. So if I write the conservation of mechanical energy between these 2 points, point 1 and point 2, right? At point 1, we know that the kinetic energy is E as given in the question, and what will be the potential energy at point 1? Is at a distance r from the center of the earth. So we can say that the potential energy will be minus gm into m by r. So this will be the potential energy at point 1. At point 2, kinetic energy will be equal to what? 0, because it is at maximum height. And what will be the potential energy? Since it is at a distance of 2r from the center of the earth, so we can write the potential energy at 2 will be minus gmm by 2r, right? So now we know the kinetic and potential at point 1 and kinetic and potential at point 2. So if I apply the conservation of mechanical energy, we can write K1 plus U1 must be equal to K2 plus U2, right? So E minus Gm by R, that must be equal to 0 minus Gm m by 2r. So by solving this, we will get E is equal to Gm m upon 2r, right? And we know that acceleration due to gravity can be written as Gm by r square. So if I replace this Gm by r with acceleration due to gravity, we can write mgr by 2. So this is our energy E will be. So from this we can say that our option number 3 will be correct. Now let's move to the question number 14. In question number 14 it says that the pressure of a medium is changed by 15.5 10 to the power 3 Pascal and change in volume is 10%. By keeping temperature constant, the bulk modulus of medium is. We know that the bulk modulus of any medium is defined as change in pressure divided by change in volume per unit volume. But in question says that change in volume is 10%. That means delta V upon V into 100 is equal to 10. So delta V upon V must be equal to 1 by 10. And question says that pressure is changed by 15.5 into 10 cube Pascal. So we can say that the bulk modulus will be 15.5 into 10 cube divided by 1 by 10. So we will get 155 into 10 cube. That means 155 kilo Pascal. So my option number 1 will be correct. Now let's move to the question number 15. In question number 15 it says that a spherical liquid drop of radius r is falling in viscous medium with constant speed. Then rate of heat produced is proportional to. We know that the rate of heat produced will be equal to the viscous force into velocity. That means power consumed by the viscous force that will be consumed in terms of heat. So if the spherical liquid drop radius r is falling in viscous medium with constant speed, so what does this mean? Constant speed means it is moving with terminal velocity. And what is the value of the terminal velocity? We know that the value of the terminal velocity will be given by 2 by 9 sigma minus rho g r square upon neta. This is the formula of the terminal velocity. And if the particle is moving with this terminal velocity, so we can say that from the Stokes law that the viscous force acting on the spherical liquid drop will be given by 6 pi neta r v, where v is the terminal velocity and r is the radius of the sphere. So if I put the values here, so we can say that the power consumption rate or heat production rate will be equal to 6 pi neta r vt into v, and this velocity is also the terminal velocity. So we can write 6 pi neta r vt square, and since vt depends on r square and there is one more r, so we can say that this will be r into r square whole square. So we can say that this power consumption rate will be directly proportional to r to the power 5. So my option number 3 will be correct. Now let's move to the question number 16.